All right, yeah, very glad to see people actually are really talking to each other and also, yeah, cannot leave their conversation. That's a very good sign. But at least, yeah, to avoid the disturbance to the speakers, feel free to actually getting back, and then, yeah, let's somehow jump into the interesting part of the afternoon. What do you see here on the screen? This is actually the new QR code. Please use your smartphone to scan it again. It's a different QR code than the morning. And then we are collecting your questions so that later we will ask your questions, throw them to our keynote speakers and all the speakers in the room. And I believe probably you have never seen and never actually asking questions to those people. This is actually a very good opportunity. So we will keep these QR codes interchangeably when every speaker finish their talk. So if you miss right now, that's not a end of the world. But at least if you have it now, that's good. Okay. So in the afternoon today, we have a different community that's probably not the most kind of visible ones to the Power Web general colleagues. And then it's also kind of very nice that we finally, and luckily, the people who have time today among the list coming here to talk about very different facade of sustainable ICT distributed system challenges. And then as you can see here, maybe this is actually all the 6 people are the new faces to half of the people in the room today. But then that's the opportunity, because then, yeah, through them, you will hear very different perspective, could be confirming your thoughts, maybe also conflicting with what you imagined before. And then for me, that's actually where every time when I have the entering the new community, that's what I'm looking. I want to be shocked, I want to be surprised, and also see something different than my general daily, blah, blah stereotypes. So in that sense, without any due delay, we will pass the mic to Martin, and I have one sentence to say to him. So in Netherlands, people like to talk about the father of something. So he is the father of distributed system. Yeah, I said everything now.
So one thing that, Aaron just made one mistake. I'm not the father of distributed systems. There are other people. Actually, I have a picture of one of them. The other thing is that Aaron did not tell me what he was expecting me to talk about. So I'm not going to talk about sustainable edge AI and ICT, only indirectly. I'm going to talk a bit about distributed computerized physical systems. And after listening to the talks this morning, I realized that everything that I wanted to say has already been said. Except I'm going to say it in a different way, and I'll leave it up to you to whether you can recognize whether it's the same or not. Okay, there's this thing over here. Basically, so I'm a computer scientist. That means that almost everything for me is in computer. You're not, by the way. But when Tesla became popular, I was thinking, oh, that's a really nice computer with 4 wheels and God knows what, because it's just a full-blown computer to me, right? With all the nasty things that a computer systems brings, okay? So if I take a look at the power grid, I was thinking, okay, it's almost a computer system. And of course, I'm wrong, okay? But that did inspire me to come up with a couple of slides to give my perspective on, let's say, physical infrastructures, for which I know that my perspective is going to be flawed at certain points because there's something nasty out there behind the distributed system. It's a physical system, and that suddenly brings a different perspective as well. And I will invite the people from this morning to take a kind of a different look on their physical systems and say, wait a minute, there's a computer system behind that. And what does that mean for my physical system? That's the reason why I'm talking about computerized physical systems. So I'm not going to talk about IT versus OT. That's all the same to me. This is one of the fathers of the distributed systems. This is a Turing Award winner, Leslie Lamport. He gave a definition of a distributed computer system, as being one in which the failure of a computer you didn't even know existed can render your own computer unusable. By the way, we experience this every day. You know, if something goes wrong, you don't know why with your computer systems. You don't know why, but it's not your laptop. It's something else, and if you've never heard about this thing before, and it will make your life can make your life miserable. The thing about this definition is that he's talking about a failure of a computer. Okay. And this is where the big deviation starts when you talk about physical systems, because there's just a bit more than just computers. This morning there was a lot of talk about security, and the message for today that I would like to convey is that we need to look at more than just security. Security, in my field of work, is part of dependability. And dependability at least covers these 5 issues, and you can easily expand them. It's availability, up and running when you need it. It's reliability, that's continuity. How long can a system run continuously without failing? It's safe. That means that when something or the system fails, nothing bad will happen. I'll leave it up to you to define what bad means. Secure. This is what we've been talking about this morning. No unauthorized information disclosure, modifications, denial of use. You could make this list a bit longer, but you get the hang of it, right? And maintainable. When things break, they can be fixed. This is what dependability means in my field of work, in distributed computer systems. Now, I try to make a translation to physical systems. Okay, available is up and running when needed. Reliable, how long can a system run continuously without failing? That's the same thing as with distributed computer systems. Safe, when the system fails, nothing bad will happen. Also the same. Secure, no unauthorized information disclosure. I don't know for sure. If I take a look at the strict physical system, probably you can leave this out. But if you take a look at IT, OT convergence, then suddenly the information disclosure is there again. And Zeki this morning already was talking about confidentiality and privacy. That's very much to this information disclosure. Modifications, denial of use, and maintainable. When things break, they can be fixed. Hey, there's no difference. My conclusion is dependability in the physical world is the same as the dependability in my world. Oh, by the way, the only hardware that I'm looking at are computers. They're really easy. If one breaks, you know that there's another one and you move everything to this other one. And it's really almost as simple as that, with a bit of exaggeration. This is about the containerization and the virtualization that was also discussed this morning. Now, let's focus a bit on this security, no unauthorized modifications, and denial of use. My claim is that the focus in cyber-physical systems is currently on attack prevention. And the only message that I want to convey today is there is more to look at. It's more than just making your systems secure in the sense that you can prevent attacks. And that's the whole dependability issue. So I really have a very simple message, and I don't have that many slides. So to me, cyber-physical systems are computerized systems. And I know I'm exaggerating, okay? But this is just my bias of looking at these physical systems. And to me, that really means that we need to pay much more attention to this dependability issue. It's much more than security and attacks. And if you take a look at what we're doing in the distributed computer systems, and now I'm addressing my colleagues in, let's say, the ICT world, the standard solutions for distributed computer systems need to be reconsidered because there's a lot of physical stuff out there. A very simple thing. We think often very binary. It's working or it's not working. Well, Leslie Lamport gave also kind of a definition like, well, it's not working, but I don't know what's causing it, you know? But if one of our computers breaks, there will be indeed another computer that can almost instantly take over. Not always, okay? But in many, many cases. This is the reason why these clouds are so reliable. There are hundreds of thousands of computers that simply take over all the time. Because if you take a look at Google warehouses, any moment there is something broken out there, except that we don't notice it. This is everything to do with the virtualization, containerization, works like hell. We don't notice that our hardware is broken. You can't do this with really physical systems. So if one of your pipes breaks, you got yourself a problem, okay? Or anything else. I don't have to tell this to the people who are looking at physical infrastructures. That's a big difference. And if computer scientists think, aha, we can just see this as a computerized physical system, well, I don't think that's going to work entirely. We have to think of the fact that there's really a physical component and more than that. But the same goes for the folks who are looking at physical systems. The standard solutions for physical systems need to be reconsidered because there's a lot of digital stuff out there and more than just security stuff. Which brings me to the following. This is what we're now currently working on with a very small group at the moment in Twente, at least I'm working now with a couple of my colleagues. Focus on consequence-driven models for dependability. So if you are under attack, who cares? Unless you know what the consequences are of that attack. That is a big difference with the standard way of that computer scientists look at security attacks. Ooh! There's a security attack, I need to do something about it. Well, maybe not in terms of physical systems, because the consequences of that attack may be not as big as you would think it would be. So it's not a binary decision. And there are many of these decisions that we need to rethink of what are the consequences that X breaks, etc., etc. This is a new thinking for, I think, many of at least for myself and also computer systems people. So the road ahead is pick your battles well. Because if we want to do everything, if we want to have a fully closed and fully secure distributed system, a computerized physical system, you're probably going to waste a lot of efforts, actually, I would say. From an attack prevention to consequence-driven analysis to, in the end, effective increased dependability. Take all the features of dependability into account. That's my plea. Readiness, continuity, safety, security, maintainability. And think about what the consequences are when something is not behaving according to your expectations. And then decide to take action or not. And I think that was my last slide. No, almost. This is always the case. We have a bunch of colleagues. This is just a few of them. And there's only one of us really doing the real hard work. You all know this. This is the infamous PhD students, and I'm just bragging about his work. Thank you very much. And I'll hand it over to you.
So as usual, please throw your questions to the QR code. So we will actually take that into account. And then without due delay, I hope that everybody actually get a nice transition from the previous one, because I think, Martin, you did a nice way, because you echoed the security and cybersecurity topics in the morning. So now we are also kind of from there going deeper into actually more diverse subjects. And then it is also nice to actually hear our university partners from Rotterdam and actually showing you very different perspective. And now we are actually entering this, what we call the sustainability and the power web topics.
Yes, thank you very much, Aaron, for the invite. It's a great pleasure to be here, and thank you for the previous presentations. My name is Yashar. I'm an associate professor at Rotterdam School of Management, Erasmus University. I'm also the academic director of two centers, energy-focused centers at Erasmus University. And the scientific lead of Center for Energy System Intelligence. This is an AI energy coalition together with TU Delft, and I'm the scientific lead from Erasmus side. So I am involved in multiple European projects. What I'm going to talk about today is related highly to one of them, MODES, which is basically developing the data layer system or data layer infrastructure for future energy markets, and what are the difficulties surrounding that. So I would like to start with reminding everyone, of course everyone knows about it, but it's just a recap that we hear a lot about AI and digitalization in energy systems, and you see a lot that is happening in the energy. From upstream to midstream to downstream, and the number of technologies and new development that you see, it's increasing day by day. And it's everywhere. It's very unlikely that you talk to people and they don't know about it. It's not only about the applications that you see in all of these three streams, but also the technologies that you see and that they are connecting with energy systems. So energy digitalization, even though that it is improving and there are great potentials, it has created a race to many industries, including the retailers. So they see it as a once-in-a-generation opportunity, and they are in this race to be the dominant player in future markets. Octopus in UK is a great example, but you see that also the local retailers are also in this race, and they are trying to be the dominant player to gain the most out of this revolution that is happening in the energy system. I'm only talking about retailers here, but of course this revolutionary transition is happening in all stages. Even though energy is not among the leading industries in this whole transition, this is a study that I really liked with BCG that they have done, that they have gone through 40 different indexes, and they come up with this digital acceleration index, and they realize that energy is not among the leading ones. So there is a lot that is still they can still gain, and they attribute it to many problems, such as that the initiatives, the digitalization initiative in the energy system, they are not value focused. They are very disconnected. The legacy is a big hurdle, and the mindset. So how can we help it out? They also come up with some boosters. And I mean, each of them, there's a big study behind it, but what I want to highlight here is their focus on leveraging data and AI. So they see that data is a big problem in energy systems, and we have to improve a lot in this domain. But why do we talk about it now? Why is this becoming a problem now more than ever? There are many reasons behind it. So first of all, there is a technological push. So we see that there are great advancement in technology, such as smart meters, IoT devices, and cloud computing. We heard about some of those technologies today, but also the integration of renewable energy. So this technological push also creates challenges in supply-demand matching, which is also technology related. Some of the push is about the revolution in the business models. So with the transition towards digitalization, there are some new types of businesses are evolving, such as energy as service, dynamic pricing, market analytics. So there are also, we need to have data and collect data for those kind of revolutions. Some of these pushes because of the policy changes, because policy is also adapting, and each new policy brings new calculation that how we can adapt this policy, how we can make the best out of this policy, and also for future policy recommendation, what are the best ways to go. But also people are becoming more aware of the importance of data, that they are the data owner, there is value in their data, how they can share data, and the public awareness is also increasing. So all of these stakeholders, all of these technological push, business push, policy push, and people changes, it has created a great momentum for data to become a bigger part of this game. And there are great challenges in this direction. For example, even though that we have started to collect a lot of data in energy systems, but there's still great data availability problems. One of the classical example is the secondary substations. So basically behind the secondary substation, there's still black box. And now with dynamic congestion management, it is becoming a big problem. This is one of the things that we are working with Stading to help solve it. At TSO level, reactive power is also becoming a big data gap, because with the implementation of more electric vehicles, more PV panels, reactive power is becoming a big element, but there's not much information at the TSO level. The other problem is data silos and unused smart meter data. So once they realized that AI and digitalization is needed, they started to collect data at really high resolution. And as we also had in this presentation by Suzanne, there's collecting more data means more energy consumption, more carbon emission, but not all of that data that they're collecting is useful. It's actually, on the contrary, only 2 to 4% of the data that they're collecting is actually being used. And there's this synchronization problem that we know data is needed, we don't know for what purpose, at what granularity, and who will need that. And that's why this is happening at very inefficient way. The other problem is interoperability challenges. We're collecting data at different organizations, different departments, but they are not synchronous. And if you even give them the data, they might not understand it. Competitiveness, when you know that there is value in the data, it could create a problem, a business problem, that the data owners or big industries can monopolize the new services. Then there is the regulatory issues. And we have been talking about this DSO problem that they collect smart meter data. It is highly important, highly needed for congestion management, yet they're not able to use it proactively, or they are not able to share it at the granularity that's needed for retailers. There are also challenges for energy community, such as data acquisition. So with all of these challenges, we want to see what are the best solution. How should we move forward? And there are many things that in this decision making we should talk about. For example, what is the data granularity that we need for each application? When do we need to share it? With who do we need to share it? And what's the value of that data? How can we tag the value of the data? What are the incentives, the best incentive, and that's not necessarily monetary incentives, access control, usage control, business case and governance, privacy, security, making sure that it is a just transition, interoperability, and standardization. Each of them is a discipline by itself. Our focus is on the first two parts. What are the incentives and how can we give value to data, combine it with market mechanisms? I want to end my presentation with two related initiatives. One is a European Commission initiative. So they have a working group that they want to have a common European energy data space, seats, and they have an article like that. It outlines the blueprint version 2 of energy data space, and they're focusing on 5 use cases: energy communities, home energy management systems, TSO, DSO, data sharing, electromobility, and renewable OM. And finally, with SAISI, we have also started to have a testbed for data sharing, and that's something that we would like to ask every single one of you to start registering. And this is for researchers, that any data that you have or of in energy space, you can share it with your researchers that of, and you can search for the data related to your research in this platform. So basically, this is a central platform that you can share. You can share the data either publicly or the private data, energy data that you have, and this could also be testbed for more collaboration. And this has a very nice feature, such as, it's a more of a LinkedIn profile that you can create there, and you can have shared project and work together. This is all I wanted to say. It went a few minutes over time. Hope it's fun.
So yeah, after we have here the background of computer science, and then we have our partner university from Rotterdam, so we have also a business flavor in this domain. Now we actually go to the Royal Telecom in Netherlands, and let's hear what KPN actually has to view on.
Yes, thank you, Aaron. Yes, Erik Smijting, KPN. I'm the research lead for 6G and Spectrum, which basically means that I work on preparing for the modernization, the complete renewal of our mobile network around 2030, and preparing for the auction that we will have to buy that spectrum. And next to that, I'm a part-time associate professor here at TU Delft in the group of Piet van Mieghem for network science. Today, I'll tell a bit about what KPN is, a bit about KPN, and also what we are doing with Edge, more like what type of service we are doing, and then I will go to the specific research that we do here at the TU Delft together with KPN and TU Delft together. Yeah, telecom. We are, what I think, in a new era already some time, and we call that the coordination age. So everything connected. And as a telecom operator, it's not only about connectivity anymore, but it's really to make sure that also the applications behind, so the devices are connected, but they use applications, and our infrastructure, not only the connectivity, but also our data centers, should be flexible and catered towards those new applications. And the networks become compute software-centric, programmable. And also I put a few words there. I think we have, Martin, maybe 60% match. I was doubting between reliable and dependable. But yeah, these are the 4 words that I used. Safe and secure, I think is a very important one. If you have all these applications running, everything connected, and there are real outcomes, real thing happening in the physical world based on what these applications are doing and whether they are function correctly when using AI also. Well, then a little bit about sustainability. We don't have reporting or results really on Edge yet, because we don't have Edge data centers operational yet. We are working on it. But you can see we have very ambitious goals for sustainability, net zero in 2040. And we are working towards really using 100% green energy produced in the Netherlands by 2030, and also exchanging energy with other companies in the Netherlands. In terms of electricity consumption, we have a big reduction of between 40 and 50% over the last 15 years, although the traffic has grown a lot. And this has a lot to do with decommissioning old systems. So a lot of the I should not say low-hanging fruit, because it was difficult enough to realize it, but it's not all really complicated algorithms or models, so that these are the things that we could do. But going to net zero, we have to reduce a lot more, and that will be more complicated to achieve, and we have to engineer more, I think, also together to realize that. Well, for us, for KPN, sustainability is much more than energy or carbon footprint. It's more. You see again security, reliable networks, but also affordable connectivity for everybody. And I think a very important one is the campaign that we started about online shaming and exclusion. So I think that is also a very important. How do we use the internet and the new technologies? So our infrastructure, really at a glance, but we are at 66% coverage of Dutch households with fiber. So that's only KPN. There are some competitors who also have fiber. So the Netherlands is really advanced in terms of fiber. That saves energy because fiber is much less energy consuming than the copper network that we had before. 5G, we have more than 5,000 sites, 5,000 base stations. So about one base station per maybe 2,000 households, to give you an idea. And in terms of edge, I said we don't really have edge data centers, but we have now 4 core data centers those are the KPN data centers, where the KPN platforms are our service platforms, our connectivity to the internet. So those are 4. In total, we had 11 big data centers, reduced it to 7 now. So 3 data centers are more used for services for businesses, and we consolidate those further. So that is saving energy. And we have 130 metro core buildings that could be edge data centers. Here we have a picture of the data centers. So the bigger green dots are our central data centers. We call them Desira locations. Zwolle, Amsterdam, Rotterdam, Arnhem. And all the other dots, the black ones and the small green ones, are these metro core locations. And yesterday we had a strategy update for the financial market, and we said, well, maybe we will start with like 10 or 20 of those metro core locations to become edge data centers. So we would invest in making them edge data center. Now a little bit into the mobile world. So 5G, this was the 5G vision that was formulated like 10 years ago, which marks a difference because with 4G was more about broadband and how we as humans use our smartphone, basically to use the internet. And 5G is really about connecting everything. So that's a huge difference. For example, connecting drones requires a much more reliable and low latency network than just streaming a video. We are doing pilots, working together with other companies. This one is about a wireless factory. So a factory producing goods. Normally you have to program each of the robots in the factory separately. What we do here is taking the controller logic to the cloud. The cloud can also be in that factory. And there are low-level commands to the machine over a very reliable and low-latency 5G network, which makes it much more flexible and, of course, saves cost and is much easier to innovate and make new products. Connected drone. We are working to have a drone service with partners between 2 hospitals to transport medical supplies. And we are working on making that into a nationwide service where you can have drone corridors, where you can control the drone via this 5G network. Yeah, so for that you need also very reliable connections, low latency, but also the regulation should be in place. One other one is data sharing. So I think data is really crucial also to AI. We have data sharing hub, we call it, providing services, for example, for sale. We provided with partners a digital twin and brought all the data from different partners so that there was oversight to do crowd management at sale. So conceptually, you can see that our network becomes a network that provides smart network as a service. So for example, the drone, here you have differentiated connectivity. So the drone needs very reliable, low latency, but also high-speed connection to have the camera footage of the drone available to the one who is controlling it. And the application doing that should be hosted at the edge to have low latency. Now, complicated picture, but roughly our business architecture for service delivery looks like that. So here you have all the physical stuff. Here you have kind of the computerized, virtualized stuff. So here all the network functions are kind of available in software, and you can give commands to that software and configure the network accordingly for different applications. The challenge we have here is that we have those many different devices, different applications, all requesting from the different types of services, and we will have to provision that all automatically. So there's a huge number of interactions between end-user devices, the network, and of course internally in the network between our network management systems. And now the big question is how to keep it safe, trustworthy, when AI is used everywhere. So you cannot really pen test your network management systems. You have a huge number of interactions with devices that use AI that can do all kind of tricky things, maybe not even on purpose. So how do we do that? So that was the starting point of having a research cooperation with TU Delft on the safe use of AI in 6G and in critical infrastructures more general. I will not list them all. You see the names of the involved professors and the PhDs. The first one is a bit more, let's say, the theoretical concept of how we can use network science to have oversight of such a complex world of AI agents interacting with each other. The second one is about cross-domain resilience of cross domains. So, for example, telecom and electricity grid. The third one is about data sharing. So AI learning needs a lot of data. So we want to have share data from different owners. How can we do that in a safe and reliable manner? And the fourth one is, well, our network has an evolution, but also cities, for example. So on a physical level, for example, you could think of where do you need what type of connectivity? But also on an application or data level, can we use maybe same standards for data or applications in our network and in smart cities? My last one is a completely different one, but can also relate to safety, and that is we are working already longer with TU Delft. There's a project which is called Super GPS, and the idea is to have a backup, an alternative for satellite-based positioning and timing services. So the idea here is to have a terrestrial-based service where you can transport time through a telecommunication network and distribute it via the base stations of a mobile network. So that would allow to have timing and positioning services independently from the satellite. With that, I conclude. Thank you.
Okay, thanks a lot, Eric. I would say that maybe to many people surprised that in the afternoon, even though we actually put sustainability, but you hear a lot about resilience. And now you can hear that even the KPM actually has a lot of footprints on this front in terms of the projects. And the collaboration with TU Delft, that's a very good example. I guess most of the people in the room probably are not aware of that. So it's a nice message. Okay, now let's wait and welcome the next speaker from Amsterdam. And Andy is one of the people actually driving Edge AI for many years. And then he has actually a very different background. We call it embedded system. And we had always a lucky kind of funny arguments that, he actually represents his own community. So it's different from the community Martin represents, but it's actually a very interesting one. Let's actually wait for.
Thank you. Let's hope it is an interesting one. Okay, so I have a very long title, but let me first start with focusing on this part and that part, AI and Edge, and the rest will become clear during my talk. So let's first start with the obvious, looking at what happened or is happening with AI. I mean, these models that are driving the AI revolution, as we are witnessing right now, they are growing like hell. Yeah, I mean, we have seen an exponential growth in the size of these models in terms of parameters, for example. I mean, current models have more parameters than there are stars in our Milky Way. Yeah. Now, with that growth, also the computational demands of these models is growing. Yeah, I mean, there's no free lunch. We have heard that before. So you need more compute power to actually use those models. Now, Susan talked about energy consumption of ICT in general this morning or this afternoon. So let me focus on AI. So what is the energy consumption of AI? And let me focus on only generative AI. So there was this nice article this month in IEEE Spectrum that projects that there are more than 5 trillion queries using generative AI. And this kind of comes down to the use or the production of 2 full nuclear reactors in a year. Now, in 5 years, this will translate to more than or about 120 trillion queries. And this comes down to around or more than 40 nuclear reactors. Yeah, so this is I'm only talking about generative AI. This is only a part of, let's say, the whole AI spectrum here. Okay, what can we do about that? Well, then I make the connection with edge. We already talked about that. There are different definitions for edge. My definition as a embedded systems person is really the far edge. So for me, the edge are the very small resource-constrained devices that we would like to use in this context. So for me, so on the left side, that is the traditional or the current situation where most of these very large models are still running somewhere in the cloud on very power-hungry computers. And what we would like to do is to move this intelligence very much close to the user on these very tiny devices. Yeah, these could be IoT devices. And doing that has a number of advantages, like lower latency, like less bandwidth, because you're not communicating with the cloud all the time, higher privacy, better privacy, and hopefully also a better energy efficiency, because you're less communicating with the cloud, but also you're executing these models on very power optimized systems in comparison to these cloud systems. Okay, so I will be talking about these very resource-constrained devices. Now, the big problem here is we have on one hand these very large models and on the other hand these very small devices. How do we fit these models on these small devices? That is the underlying problem here. And many people in our domain are focusing on what we call compression of these models. And there are different ways shown on this slide to compress these models. Basically, you either lose information, so you get rid of some parts of these models, or you compress, or you have less precision in these models, or you generate a simpler model out of the bigger model. Yeah, so these are all ways to compress these models. And the cost here is accuracy. So you will lose in accuracy. So the question we are kind of trying to answer here is, can we actually fit these large models without compressing? Well, clearly this is a rhetorical question. So of course we can, and I'll show you some examples of how we do it. So this is one piece of work we have done. That is where we actually try to, instead of using an out-of-the-blocks kind of neural network, we're trying to make one ourselves, tailor it to the device we would like to run the model on. And we are doing that by kind of an optimization process where we, on one hand, optimize for accuracy, so make the model as accurate as possible. And on the other hand, we optimize for energy consumption, for memory footprint, and so on. Yeah, so we're trying to search for different model configurations that will meet all these requirements and will definitely fit on the target platform, hardware platform. And I will not talk about how we actually do that, but we have all kinds of optimization processes there, and that's called multi-objective optimization. Well, when we found, let's say, a model that actually fits a certain hardware platform, then you have to take care that you are executing it as efficiently in terms of energy efficiency on the platform itself. And there you can actually exploit the fact that there is a natural affinity between the different parts of your neural network and where they should be executed on your platform. Because even these small devices, they typically have multiple computational resources like general purpose GPUs, CPUs, and a simple GPU. And different layers fit better onto different types of underlying processors. And you can actually exploit that. So we actually do an optimization again to find which part of your neural network fits best. And we have a very efficient switching mechanism that switches, let's say, the execution per layer on different devices where they fit best. Yeah? And by doing that, you end up with an overall very energy efficient execution of your entire network. Now, what happens if your big neural network actually does not fit on this single small device? Well, what you can do then is cut it into multiple pieces and then have multiple of these smaller devices, each executing a piece of that very big neural network in a collective way. And within every small device, again, you can exploit the fact that you have multiple computational resources. Now, for that, we have built an environment that basically automates this whole process. So you start with a definition or a description of your very large neural network. On one hand, a description of your underlying platform, so which devices are there, and a specification of how you would like to cut this neural network. And then this environment does everything automatically. So it will cut the neural network, it will produce the code for each part, and it will actually deploy the code on each separate device and will arrange all the communication and so on for you. And doing that, you can actually also explore different cuttings. So you can explore different mappings. So how granular, the granularity, for example, of how big all these pieces should be. And you can do optimization again there. Yeah? So you can try to find what is the best, let's say, distribution of your neural network over your underlying platform. To optimize, for example, again, for, let's say, energy consumption per device or memory consumption per device. Now, let me make a connection to, for example, Maarten's talk. Because if I do this distributed execution on multiple edge devices, clearly these edge devices are not reliable. Yeah, because, I mean, these typically are battery-operated devices, so you could run out of battery, or, I mean, they might be mobile, so you could move such that it's not connected anymore. So what do you do in that case? So we have also worked on methods that are trying to do this in a robust way. So by splitting these neural networks in a very smart way and doing replication of those parts, and only those parts, so it's very selective, that are very important for, let's say, obtaining accurate result of your neural network. So we do very, let's say, selective replication of those parts. And by doing that, we end up with, as is shown over here, with very robust results. So actually, I would like to just focus on this one, because this is kind of interesting. I have 4 edge devices over here, and I have 3 of these failing. So 3 out of 4 devices are failing. And what you can see is we are still able to get almost the baseline accuracy if we do this right. Yeah, so we can have a very, very robust system. Now, let me finish off, and I would like to mention one famous law, call it law, Jeffen's paradox, because what we are trying to do here is make systems more energy efficient, clearly. Now, because of that, of course, there's this risk that there's more demand for these services because we are making them better. Yeah, and that will, of course, nullify everything we have done. And this is what we call Jeffen's paradox. There's no easy solution there, but still, it is something to consider.
Thank you. Okay, yes. I guess one thing to notice is if you have questions to Andy, definitely feel free to actually scan the QR code and then put your question here. This is actually where you can throw a question to all these speakers. And then I think after Andy, we will have the other speaker. Now we actually move slightly back to TU Delft's research regime, but then this time we actually have a very different community representing different research profile from TU Delft. So Justin is there waiting, and then I think many people heard about the agent AI, right? And this is actually where we actually give opportunity.
Thank you. Hello. Thank you very much for inviting me, Aaron. One of the previous speakers mentioned that he didn't get any topic from Aaron. In my case, Aaron gave me a very specific topic, namely talk about AI and power systems. In fact, I had to think about it, because I know very little about power systems, I must admit. But I said, okay, let's take on the challenge. So last week, I've been reading about power systems and how AI has been explored in power systems. So I will give you a review of the cutting-edge research on AI for power systems. At the end, I'll then reflect on future directions. Okay. So my name is Justin Dowels. I'm working in this beautiful building, a tall building on the 17th floor in the Signal Processing Systems group. And so let's discuss AI in the context of power systems. I've organized my talk in multiple sections. So first I will discuss generative AI, then agentic AI, and then the combination of both, generative, agentic AI. At last, I will discuss future directions. So, who has never used ChatGPT? Nobody, right? So you all know ChatGPT. In fact, I asked it some existential question. I asked it, who are you? Well, I asked actually, what are deep generative models, right? Well, it says it's a class of machine learning models that are designed to generate data that resembles a given data set. So you give it data, maybe you have taken pictures on campus of buildings. That model will generate similar buildings that look like TU Delft buildings, but actually they don't exist. But they look like TU Delft buildings. So mathematically, it's actually a conditional distribution. You give it the prompt, it will give you an answer. You give it the same prompt, it will give you a different answer. Slightly different. Actually, a probabilistic distribution. Okay. And then I asked a different model, Stability AI, Stable Diffusion. I asked to generate the Great Wall painted by Van Gogh. It gives you multiple versions, because you can ask the same question multiple times, it gives you different versions. It all kind of looks okay, but if you look closely, you see here is not quite correct, perhaps. You have here like a second lane, which I don't think is actually there in reality. So it's always wise to check the output of generative AI models, whether that's for art or for power systems, for weather application, whatever it is. You should check the output, because you cannot just blindly trust generative AI. And that's just one illustration. How to use generative AI for power systems? There are at least two families of applications. One is to generate what-if scenarios for planning operations. For instance, different weather conditions. That's one application or one scenario. Also, it's useful to generate synthetic data. Let me first explore the what-if scenarios. Could be load, demand profiles. Could be, as I mentioned, renewable power outputs, depending on weather conditions. Electric price trajectories, electrical vehicle charging profiles, etc. So you can use generative AI to generate potential scenarios, which you can then use to optimize your systems. Synthetic data. I think we've heard about data. It's hard to get data. You could, in principle, use generative AI to generate rare events, to generate potential faults that you can use to improve your fault detection systems, which has been done in multiple applications. Can be used to generate potential attacks when you want to make your systems more robust against attacks, cybersecurity attacks, and also can be useful for anomaly detection. That's another use case. Foundation models. Of course, if you've heard about ChatGPT, people are thinking of building such a model for power systems. The idea is you feed it with lots of data, of grids. You train it in a self-supervised way, meaning without labels. And that should be useful for downstream tasks, maybe to predict the flow of power, to maybe manage your assets, etc. So foundation models could be useful for power systems, and that has been explored in some papers. That's something that is emerging in the line of like large language models. Agentic AI, very different approach to AI, based on the concept of agency, the ability to sense the environment, to make decisions and act. Multi-agent systems have been used in power systems for a while, for all kinds of applications. So each agent represents an entity, could be a load, could be microgrids, could be market players, etc. That has been used for demand and supply, balancing, grid security, etc. Now, it gets really interesting when the agents start to learn, oftentimes by deep reinforcement learning. They get reward feedback, and that's useful for cases where maybe it's hard to design a global optimization problem. Now, here are some applications of those multi-agent reinforcement learning systems or ideas for grid control, frequency control, voltage regulation, energy management, and fault restorations. In fact, some of the posters discuss some of those topics. Now, it gets really interesting when you combine the generative AI concept and the agents. Now, the agent can start imagine potential futures, potential evolutions of the microgrid, what could happen in the future. And that you can combine them, of course, with decision-making, autonomy, etc. That's how you can bring both together. And that idea is being explored, for instance, in a paper which appeared a few months ago called Power Agents from Harvard University, Zhang and Xie, where they then combine the two aspects, the generative aspects, agentic aspect, and this kind of system is called cognitive energy systems. Of course, the human stays central, right? So the agents are viewed as recommenders, as conversational assistant that can monitor the power system, can suggest actions, can spot problems, and perhaps make some low-level decisions. But in the end, of course, human operators remain responsible and have to make the critical decisions. Now, future directions. Of course, this is still, I would say, very early days. It may take 3-4 more years, maybe 5 years before agentic AI can be applied to power systems. There are many questions. For instance, explainability. How do agents make decisions? Scalability, can this be scaled to grids or multi-energy system where you have gas combined with electricity and transportation? How about robustness? How can such systems cope with uncertainty? Of course, also important is testing. Can we define standard tests to compare different systems, classical systems, and of course, and also the multi-agent systems, and the generative AI systems. With that, I would like to end.
Yeah, thanks, Justin. And I guess what Andy and Justin mentioned, I guess the takeaway for many of the power engineers today is that, those are not probably the problems you are facing nowadays, but then this could be the problems when you are embracing AI in the upcoming years. So I guess at least we want to actually show you what is actually the struggling that computer scientists we are handling now in this forefront of AI and edge AI. And then let's also welcome the final speaker of today. And then I would say he's a good friend of mine working in civil engineering, and he's a computer scientist. So you are going to hear actually a very different type of story, because nowadays it's not AI is everywhere, right? But then at least we can actually see a different picture and different case from you. So thank you.
Yes, absolutely. Thank you. Can I have that? I wish I were a computer scientist. I'm an environmental engineer by training, and I did my best to then move a little bit to computer science. And I work in that ugly building over there, civil engineering, Department of Water Management. And as an associate professor, I teach AI, and I also do research in AI, many different applications in the water sector. And I'm going to talk about sewer systems and networked critical infrastructure, not as cool as power system, but we do our best. And large language models. These two words usually don't mix, but maybe they do. Let's see. Okay, so for those of you who are not very familiar, sewer systems are very critical for sanitation and, of course, flood management. Extremely expensive infrastructure. And we have many pipes in the Netherlands alone, is 100,000 kilometers. And we spend $1 billion almost every year to basically do asset management and rehabilitate the systems. And a very key thing to do is inspection. So that's more or less how it works. You know, you will see people sometimes going from manhole to manhole in our streets. Usually each pipe is inspected once every 5 to 10 years. They push down the scrollers, can be more or less sophisticated, and then you have people either on place in those vans or even in their office then checking these camera feeds usually, but also some other sensors are deployed, and then assessing the quality of the pipe and deciding whether to change it or not. A very important thing to do, a very tedious thing to do. So people have been using a lot of computer vision and AI already to help them assessing, quantifying the defects, identifying the defects from these CCTV feeds. Several startups already working in the business. But this is the future, which is closer and closer to the edge. So 10 years from now, maybe you will see robots crawling inside the sewers and living inside the sewers as well. So they can give us, a much cheaper, let's say, also in terms of energy, hopefully, asset inspection at very high frequency. So this is one of the main directions. You see already, this is from ETH. They have their animal robot, which has been deployed in the sewer systems of Zurich, I guess. And there are several European projects. The last one is this Pipeon.eu, and they really hope to push this forward in the coming 5 years, at least in the European Union. Now, they're thinking a lot about how to make these robots. And my interest, which is starting, is, these robots must have brains, right? They need to be very autonomous. They need to make decisions. And if they are deployed somewhere in Florida, they need to escape also alligators, as you can probably see from that AI-generated picture. Now, this would be like a research direction that I might start. And I wanted to see with what we have already, which people sell us as reasoners, like these LLMs, whether there is a possibility of using this type of models to actually see whether we can build robot brains based on those. Why? Because they say they can reason, and they have these agentic capabilities. Already Justin mentioned them before, and they can already process this type of CCTV images, this feed. Some of them are vision language model, so we can already test basic capabilities. Now, what I did in this preliminary work with my colleague is to test, some of the models out there, VLMs. You can recognize some of them there, by feeding them images from these CCTV cameras, and also a very detailed prompt to make them work as expert sewer inspectors, asking them to recognize in these images whether there was a defect or not, 5 different type of defects, and then one non-defect class. Then, also provide how confident they are about the prediction they make to see whether they are aligned, and also provide, a description of what they're seeing to check for hallucinations. Now, these are the objectives of this study. These models have not been fine-tuned on the problem, so they're like in the wild, sort of zero shot. But, we see so much hype, and it means that, there is a lot of, expectations about them. And also wanted to check how different parameters affect accuracy and whether these confidence scores are indeed aligned with the actual prediction and see the hallucination. Now, there's not much time, so this is basically an example data set. We use only 100 images because we did run a lot of experiments. You can see some of them there. Some typical problems that we have, also typical of other type of infrastructure built with this type of material such as concrete. Now, these are the results that we see. So think about the edge. So these are different large language models, and we see that performance improves quite a lot with size. And size is a problem, of course, when you talk about edge, which is not great. If you see the smallest model, we're still talking about billions of parameters. In the previous presentation, we saw models at the edge of around millions of parameters, so that's going to be even more difficult to fit, and this performance are not really that good. Once you put the proprietary model from, let's say, OpenAI, ChatGPT, those are supposed to work much better. We see that indeed performance improve, and the best model of all is this GPT 4.1 mini, which is actually not the best model that they have. So you can see that performance actually plateaus. And this, of course, is not deployed on the edge, so this is theoretically what we could achieve by using today's model. not great. Don't have much time to go through this. This is interesting because there is no alignment between the prediction that these models make and the confidence that they assign to those predictions. But if you use O3 high, so that was the largest model that we used back then, which has this reasoning capability, once we push this reasoning effort, at least we see that even though performance don't improve, there is a much better alignment. So when they say they are confident about the result that they predict, actually it is more likely to be correct. Maybe there's no time about this, but we check the hallucinations and some of them are really bizarre, but sometimes they provide predictions which make sense, and even human might have made a mistake in that case. If you want to see how these things work, you can scan that code. There should be an Hugging Face app running. You can see how these systems are good at making, or not good at making predictions. Lastly, there is no GPT-5 here, right? GPT-5 came about after we made this paper, and you can see that the performance is still there, plateau, right? And they say it's PhD level. Of course, this is very broadly, but I can say that our PhD working on the same problem with, much more difficult, 18 classes, not 6, and that's a model of 20 million parameters, very specific, is actually doing much better than that, as you can see. So, yes, go PhDs. And the idea then is like, okay, if I want to develop this system, right, should I fine-tune an existing LLM, or should I instead devise something completely from scratch? Luckily at Delft, there are many experts that I can consult, and maybe I will start doing this soon. Basically, that's all I have. Thank you for your attention.
Maybe Alex, can you show the questionnaire slides? Yeah. So, by the way, now we are collecting all the questions you can have. Please feel free to scan here. And then the natural step is that we are going to head into one of the interesting, probably highly expected parts. It's about the panels. And then the panel today, we would like to have it in a massive way. This is the first experiment we try. So all the keynote speakers, we will somehow help to arrange them on the stage. And then that means that it's a kind of a luxury experience for the audience. So now you can actually throw your questions, and we will also pick up some of the questions you throw to us in the morning and in the afternoon. So then let's actually have also kind of interesting debate in the upcoming hour. And then during the current time, I guess we have 5 minutes. Everybody who want to visit the restroom, want to fetch a coffee, feel free to go ahead, and then we will arrange the seats here for all the panelists. So yeah, 5 minutes.